Hello again, I'm Dr. Bettina Heinz, here to tell you some more about chemistry, particularly the topic atomic theory. We are now doing part 3 today, but I have a little leftover from last part. That means the important concept of the nuclear atom detection by Rutherford and his co-workers early the 20th century, and that is the gold foil experiment. So let's look at the gold foil experiment, and let's give some thanks to gold for being such a wonderful element, such wonderful metal which has beautiful properties such as extreme malleability. Gold can be ground to a very fine film that is transparent, like saran wrap in a sense. And it was used by Rutherford and his group to do the so-called gold foil experiment. So we have here in our little diagram the gold foil here in the middle, and we have an alpha source, a natural radioactive element that releases alpha radiation. That means alpha particles which are particle rays, meaning helium nuclei that are bombarded or pass through a slit and then targeted onto the gold foil. Now what one expected was that all the rays would be reflected, because one thought gold is not penetrable for these, by these rays. So just like shining a light on a surface, everything will be reflected. Like a shiny surface, metal surface. Definitely we would expect everything to be reflected. But somehow something else happened. Well, in order to detect what was happening, a circular film was placed around the setup. It could have been also a fluorescent screen made out of zinc sulfide, which gives light, produces some flashes of light when particles or some material hits it. But a photographic film is also very good, because when you develop it afterwards and spread it out lengthwise, then you can see that most of the exposed parts are right behind the gold foil. So everything is illuminated here after you develop. And the other parts are more or less dark. We have some bands here left to right to the major area, and a few isolated bands here on the outside. Now how can we interpret this interesting phenomenon? Well, it shows that the gold is transparent to particles. Somehow they pass right through. Why is this? By the way, usually a lead block is used to protect any stray radiation. Lead is impenetrable for radioactive rays with the exception of gamma radiation, but particle rays are blocked by this material. Now if we look carefully and look sideways now onto the gold foil, the thin film, and we see sort of an array of atoms lined up, then the alpha particles, which are helium nuclei with atomic number 2 and mass number 4, having lost their electrons. So they're positively charged, that's very important. So they're going right through the foil. Most of them occur here and expose that part of the film or illuminate that part of the fluorescent screen that is right behind it. Now occasionally we have some exposure points here on the periphery of this main area. That means somehow the positive particles are deflected, bent away from their straight path, and only a few are on the extreme areas of the film, like here and here, which indicates that sometimes, but very rarely, the rays are totally reflected, as we can see here in our image. Now this was extremely interesting to these researchers. That means that the atom is practically empty. That means most of the mass of the atom is concentrated in a tiny, tiny little area within the big atomic environment. So that means most of the mass is concentrated on a pinhead, so to speak, and the atom is surrounding that area with practically nothing except electrons. So when we have a head-on collision between the two nuclei, the alpha particles and the gold nucleus, then of course we're going to have a crash up. That means, well, no destruction hopefully, but the alpha particle will be bounced back from where it came from, at an angle of inclination, of course. So this is the nuclear atom. And after this, people could really study the electron shell. And the electron shell, which is the area surrounding that nucleus, is what's so important for the chemist, because we want to see whether the electrons have any type of orderly structure in their environment, in their home base environment, which is the electron shell of the atom. So with this, we want to conclude the Rutherford experiment was really extremely important for the further studies of atomic structure. So these are the topics that we want to discuss today. There will be some overlaps, I hope you forgive me, but at least you have a nice list that you can use as a review and as a guideline of what areas were covered in this whole subject, atomic theory. So spectroscopy played an important role in knowing about the electron shell. And we also learned a lot about the nature of light by looking at electron transitions within this electron shell. Electromagnetic radiation, the concept of the photon, which is a little energy particle or light particle, the speed of light, Planck quanta, de Broglie material waves, spectra, which will be mainly covered in section 4, part 4 of this topic, the different types of spectra, properties of subatomic particles. We already discussed quite a bit in the part 2 segment of this subject matter. Particle wave duality of the electron. That means the electron is not only a particle but also a wave. And we have already discovered that in the last segment with the cathode rays and the canal rays. And the uncertainty principle postulated by Heisenberg in Germany, that means that you never know exactly, because of the duality of the electron, where the electron is at a certain given time. So movement and location cannot be determined simultaneously, or the momentum of the electron and the exact location are always uncertain. Here we have a view of the different atomic models from the more historical one of Thomson, who, remember, studied, did mind, or let's say revolutionary experiments that led to the EM ratio of the electron. He postulated that the protons and neutrons, remember protons were discovered by the canal rays, so he postulated that the atom was sort of a colorful mix of both particles, like a raisin cupcake or blueberry muffin, whatever your appetite is. This is sort of a wild interdispersion of the two fundamental particles. So this model, of course, did not hold water eventually, right? We all know that. Then today we will mainly, or in this episode, we will mainly talk about Bohr's model, Bohr's atomic model, that was a result of the spectroscopic findings that other scientists made. So he postulated that the electrons are orbiting in distinct shells around the atom. Similar, sort of a far-fetched concept would be similarity to the planetary system, with the sun in the middle being the nucleus and the electrons being the planets, so to speak. Then the most modern atomic model is the quantized model, where we don't even know where the electron is. We only know the probability areas. So the electron moves in certain stable probability zones that were later determined by wave mechanical models. Now, what was very intriguing to many scientists were the de Broglie material waves. He determined that anything that has particular nature and is moving at fast speeds will give off some radiation. So you can even use this formula to calculate whether you give off any electromagnetic radiation. You just have to put in your mass and the velocity at which you're moving. The h is what we call the Planck constant, derived by Planck, and we will learn more about that later. So it's a natural constant that is found in many of these formulas. Here is a little history about this, which we don't want to go into. And another important scientist is Schrödinger, that developed a wave function for the electron, which is, of course, associated with hydrogen. Hydrogen was the easiest to study because it was a one-electron system. So that electron would be in a ground state around the hydrogen nucleus or in a certain ground orbit, but could be excited to higher orbits. And when it goes to higher orbits, it would fall back down to its ground state and give off electromagnetic energy. He postulated, with the help of his wave function, and I have it here, but please do not worry, you do not have to know this. It is actually called the Xi function. So here on my PowerPoint slide, I've changed that. Psi, remember, is something else. So this is the Xi function, like Xi function. So this is a very complex function, but with this you could calculate various energy levels for the one electron system, and they became like standing waves, closed waves, similar to musical waves at certain intervals of a string position. So there was a lot of regularity. So he considered the electron to be a particle, and de Broglie sort of led him to this idea. Now here's a little cat. There is an interesting story called the Schrödinger cat. It is sort of a paradox that was discussed a lot, and you can have fun looking that up. I guess it's not enough time to go into all this at this point. Now Planck, Max Planck, developed the the Planck constant, of course, because it's in his name. He was interested in looking at energy levels of the different orbits, and he has this formula of how to calculate exactly the energy content of a given electron orbit. So E equals the constant times Z, which is the atomic number, squared, and N would be any integer, or the particular orbit we're dealing with, like the first, second, third, fourth, fifth, etc. orbit. So you could calculate the energy for any shell, any orbit, with the help of this equation. For instance, the fourth orbit of the hydrogen atom, meaning the electron involved in the hydrogen atom, would have this amount of energy, 4.903 times 10 to the negative 18 joules, which is an energy unit. Here we see a spectrum, which is called a continuous spectrum. It's like a rainbow spectrum. It's produced by the sun, stars, or incandescent light bulbs. It's an uninterrupted blend of colors, polychromatic, and we do not see any distinct energy levels here. That's why we have a smudge of the different colors. Now this is the visible part of the spectrum. that is for us visible, but maybe invisible for somebody else. Different animals, different eye types. And here we have what we call emission spectra. That means the chemical itself, when it's excited, the electrons jump to higher orbits, and when they fall back down, they release certain distinct forms of energy. And here we have the hydrogen spectrum, the mercury spectrum, and the neon spectrum. Now the hydrogen is very straightforward as we see. We see a red line, a green line, and two blue ones. Notice that the distances get shorter and shorter as we go from to shorter wavelengths, meaning higher frequencies, meaning more energetic energies. Mercury is complex, as we see. Neon is even more complex. If you would work with these spectra even further, you would get sub-energy levels visible in the spectrum, and that will be discussed in our fourth part. Here we have the reverse of the emission spectrum, a so-called absorption spectrum, where we see dark lines on a rainbow background. Now what does that mean? Those are substances that absorb their energy from the light source, and that means the observer will see black areas or cutouts, in a sense, at that position where normally the emission lines would be. Fraunhofer means those are the gases or the excited molecules or elements around the sun's environment. Here we see the different spectra. This is going to be discussed more in the next section, but you see we have a light source here, a prism that breaks things down or disperses the colors into its components. Now this picture here on the bottom right is an electron diffraction pattern, just like a normal light diffraction pattern. So you see the electron really does have wave characteristics. On the left we have a crystal diffraction pattern using X-rays. Now the spectra here, you will remember we saw just the hydrogen spectrum. And the hydrogen spectrum is this one here, the top right one. You see how the lines are very regular and they behave almost in a logarithmic fashion. They get smaller and smaller. So this is called the Balmer series because this is the visible spectrum of hydrogen. Other people produced other spectra, like this is the Lyman series. It is similar to the Balmer series, only more contracted. It relates to the UV section of the electromagnetic spectrum, and here we have an example of an infrared spectrum of hydrogen. The lines are the same pattern, only more spread out. We have more infrared spectra that have different names as well, but this is what it actually means. That means the electrons, after they have been excited, or it has been excited since we're dealing with a one electron system, and it falls back into the different energy levels, the different main shells, K, L, M, N, O, P shell. These terms come from the spectroscopy part of research. So if they go back to the first shell, we have UV. If they go back to the second shell, we have the visible part. If they go back to anything higher, we have the infrared. Now, the electron shells, or the spectra, in a way are a reflection of how the electron shells are organized around the atom. And that is the wonderful correlation that we have here. Now in this illustration, we show the orbits equidistant from the nucleus. Now you can calculate the actual radius of the shells and the energy of the shells with the help of different formula that have been also developed during this time. But I made them equidistant for illustrative purposes. So we have the names of the shell. The N equals 1 means the first shell, N equals 2 means the second, or L shell, and so on. Now the electron can be excited with any means, any type of energy. So it goes to higher orbits. And as it falls back down, then we get the electromagnetic radiation. And if you use that and diffract it through a prism, then you get the spectrum. And if we look at the energy of these orbits, these are the differences, the gaps of the various shells, energy-wise. And notice that this pattern reflects the spectrum of the hydrogen, with the big gaps, and then they get smaller and smaller. So if we go any further, then everything becomes sort of fuzzy. That means we don't have distinct energy differences anymore, and that's the state where the electron leaves the vicinity of the atom and is random, can have total freedom to move around. It doesn't have to be in distinct levels. But as long as we are in the environment of the atom, we're fine. We're fine and organized, so to speak. Now, the differences of the energy levels will give you the energy radiated, or the frequency or wavelength of the energy given off. So the deeper the transition of the electron, the longer the wavelength, the shorter the frequency, the more energy is involved. And here we see it again, and calculations can be made. If you want to calculate the wavelength, which is lambda, you can do that with the equation derived from E equals mc squared, which is the Einstein equation. A photon is always a Planck constant times the frequency, h times nu. And frequency times lambda is the speed of light, c, small c. And then you can do some interconversions, and you get the formula lambda equals Planck constant times speed of light divided by the energy. So you can get the energy or you can get the lambda. But you have to know 3 of these in order to calculate 1. Now, interpretation of the line spectra, we can do again. So the energy that is absorbed will be an endothermic process. As the electron goes back, we have an exothermic process, or energy is given off in the form of electromagnetic radiation. And Bohr, a very famous scientist in Denmark, Niels Bohr, he was very interested in these energy level changes and postulated then his particular Bohr atomic model, that the maximum amount of electrons that you can have in a certain shell is governed by the formula 2n squared, where n equals the particular shell number. So that means the first shell can only have 2 electrons, the second shell can have 8, the third can have 3 times square is 9, times 2 is 18, and so on and so on. Here are some values of energies calculated and radii calculated for the electron in various energy levels. So we have the different shells again, the number. This is called the main quantum number of the electron. The shell number, or shell letter, depending on the old spectroscopic designation. The energy, the radius in angstrom, which is 0.1 nanometer. And here, oh, sorry, and this is the radius also in picometers. So the nanometer is somewhere in between, apparently. We have here an overview of how the so-called wave mechanics came about. We have Planck's relationship that the energy given off is a multiple of his little photon, which is Planck constant times the frequency. Bohr determined that the energy is related to the so-called Rydberg constant divided by n squared, meaning that the energy differences between different orbits determine in the end what wavelength we have or frequency we have. And this final equation, which allows you to calculate the wavelength from the energy transitions, is given by this formula. And the Rydberg constant, the RH, is a constant which is the energy released when an electron comes from infinity and goes back to its ground state, meaning for hydrogen it would be the first shell. That's why we call it RH, because we can also have our helium, our lithium, whatever. Then we have Broglie, remember? De Broglie with his particle wave equation. We have Einstein with his mass defect, and also with his photoelectric effect. That means energy can interact with particles, and particles can interact with energy. So energy can loosen the particles. The photoelectric effect. And Balmer, who also developed this equation, but in a little different form. So Bohr used all this information to establish that particular theory. Here we have some heads for you. Niels Bohr in Denmark, the Bohr atomic model, Einstein, the photoelectric effect and the mass energy relationship. Erwin Schrödinger, the one who developed the wave function, which will lead to different probability areas that we will talk in the next subject, in our next topic. Balmer, a Swiss teacher, not an official researcher, but very important in his work that provided us with a lot of helpful information to continue on. And Rydberg, a Swedish scientist who determined the Rydberg constant, or who established it. Here we have how mass and energy is related. We don't want to go into it too much. In your spare time you can study this in more detail. E equals mc squared. That means when energy is absorbed, the mass decreases. If energy is released, the mass increases. So you can do some calculations and talk about the mass defect, which is so important for nuclear chemistry. And here we just see again how the spectra relate to the energy transitions. And with this, I want to stop here and see you next time.